Okay, good afternoon, everyone. Welcome to the Spectral Graph Theory course of this second semester 2021. So this course has an official website, which is this one you're seeing right now on your screen. It contains a link to these lectures on Microsoft Teams. It contains a link to the playlist on YouTube, which I will be posting the lectures which are being recorded right now. It contains a description of the course, which I hope every one of you guys have already checked. It has a sort of tentative schedule of classes with the topics that will be covered. It also explains how you guys are going to be evaluated, and it contains some list of books and resources I will be basically using to prepare my lecture notes now. The course also has lecture notes, which right now contain 93 pages, but these are an adaptation of lecture notes of a course I offered 2 years ago, and I will be changing these. So right now they're not completed. For example, the section 3 will be significantly expanded. Section 1 actually has moved, and this is because I decided to start today's class on section 2. So actually, this is already a snapshot of the updated version of the course notes, and I will keep updating this course notes on the website. So whenever you are going to study, please check the website again to get the latest version. Right now, you're seeing October 14th version. Currently, I have October 19th version, and so on. Okay. The tentative schedule is also here. Here there is a spot for me to post the assignments you guys will be solving during the course. However, as I just mentioned, I think I will be posting these assignments on Microsoft Teams, but well, maybe I will post in both places, and that's okay. Now, if you have any questions during the classes, you're free to open a microphone, ask a question, or you can ask a question on the chat box here on Microsoft Teams. All right. So, what is this course about? Let me actually add a page here. So, hopefully all of you know what a graph is. If you do not know what a graph is, let me know, and we should have a conversation after today's class. So, this course is about what you can tell about the combinatorics of a graph. So let's say this is a graph. So for example, this graph has a triangle, it has a 4-cycle. This graph might have a matching or not, a perfect matching or not. This graph might have certain connectivity, a bunch of properties, chromatic number is, I don't know, 3. So this graph has a bunch of properties, combinatorial properties that you've heard about, that you've studied in other courses, algorithmic properties of the graph. And this course is about relating the combinatorics of the graph to, let's say, the linear algebra. And what do I mean by that? It means that, well, all of you know, I'm sure, that when you think of a graph and you put it in a computer, your computer actually, well, often uses a matrix to represent the graph. And there are several choices of this matrix. The matrix that we'll be working on for the next, I don't know, half of the course is the adjacency matrix. So let's say this is vertex 1, 2, 3, 4, 5. So I am going to write here a matrix with 5 rows, 5 columns, right? They are indexed, rows and columns, by the vertices of the graph according to the numbering system I just chose. And I will be putting in this matrix zeros and ones to represent whether or not the vertices are adjacent, meaning whether or not there is an edge between the two vertices. So for example, between 1 and 2 there is an edge, which means that here in the 1, 2 entry and 2, 1 entry, I'm going to put a 1. Between 1 and 3 and 1 and 4, there are no edges, means that here there's going to be a 0. And also here, And between 1 and 5, there's an edge, which is given by this guy. And there is typically, for all graphs that we will be working on in this course, there won't be loops. Things like that are not going to appear. Also, there won't be double edges. Reason why here always going to be ones and not 2s, 3, 4s, or whatever. And because there are no loops, between 1 and 1 there are 0 edges, so this is also a 0. And then you can come here and complete the graph if you want. So the diagonal is always going to be zeros. Okay, and you can simply put your remaining entries here, right? So I am simply completing now my graph. And this is the adjacency matrix of this graph, okay? It is, so for most of this course and for our practical purposes, it has 0 diagonal. It is a 0-1 matrix, and it is symmetric. And this is very, very important for us. And so basically, the topic of this course is to relate combinatorial properties of the graph to things that you can say about this matrix by looking at its eigenvalues and eigenvectors. Okay? And we will see several examples of properties of graphs that are determined by just looking at the eigenvalues, for example, or by looking at eigenvectors, and we will see actually important applications of these things that you can only do to a graph if you actually examine this eigen things of the adjacency matrix, and by simply looking at the combinatorics of the graph, you actually suffer a little bit more. All right? So two comments now. So we'll see several applications, but I want to make 2 comments now before actually starting, let's say, the official topic of today's lecture. So today's lecture, it was originally planned that I would talk about power series, but I decided that it was not very natural to start a course on spectral graph theory by talking about power series. So if I think that it is needed to discuss power series, I will do that later. Today's course will be about symmetric matrix. In particular, I will show today that symmetric matrices are diagonalizable with real eigenvalues and orthogonal eigenvectors, which is something you guys might have seen in your linear algebra 2 course, but maybe you haven't, and this will be very important for us today. So apparently we have a visitor just wanting to join us. So I advertise this course on the web, and there might be some people attending this course. Right now we have someone which is well, I just admitted to the thing, but, well, anyway. So the topic today will be to show that symmetric matrices are diagonalizable, as I just mentioned. But before that, I want to kind of give you guys a hint of what is the connection between adjacency matrix and properties of the graph. So the first thing is powers of a count walks in the graph. And this is quite important. So you can see that this is A is equal to this matrix. This is, of course, the same thing as A raised to the first power. And you can interpret these entries as telling you that there is exactly one way to go from 1 to 2 in one step. So the zeros and ones are telling you how many ways you can traverse your graph to go from the row to the column in this many steps. Now, if you take the second power of your matrix, if you compute A squared, you look at this matrix and you compute its squared entry. Let me simply, let me see if I can do that in a smart way. I think I can. Great. Apparently I cannot. I was hoping that this would work. Why it didn't, I have no idea. Anyway, whatever. Now simply imagine that you're computing the second power of this matrix. Okay, and let's look at the first entry. So the first entry of the second power is going to be the first row here multiplied by the first column, and the result here is going to be 2. The second element here in the first row is going to be the first row times this second column, and the result here is going to be 1, right? Because this 0, 1, 0, 0, 1 times 1, 0, 1, 0, 1 is going to be, this guy is going to hit this guy, and the result is 1. Now, this times this result is always going to be 1. This times this one, the result is going to be 1. And this times this result is always also going to be 1. So what these numbers are telling you, so this is vertex 1, 2, 3, 4, 5. The interpretation is that in 2 steps, which is the power of the matrix, how many ways can I traverse my graph to go from 1 to each one of these guys? So from 1 to 1, there's exactly 2 ways I can go in 2 steps. The first way is to go from 1 to 2 and then come back. The second way is to go from 1 to 5 and then come back. And each one of these ways correspond exactly to the 2 ways the first row hit the second column when I perform this multiplication. Now from 1 to 2, there is exactly 1 way I can go in 2 steps, which is to go from 1 to 5 and then 5 to 2. And similarly to all the verses of this graph, there's precisely 1 way I can go from 1 to them in 2 steps. And all those 1 ways are represented by the fact that this product here was actually equal to 1. So if you look at this graph, you will see that there is no way you can go from 3 to 4 in 2 steps. Because if you go to 2, then there's no way you can hit 4 now. If you go to 4, there's no way you can actually perform a step and remain at 4. Okay, so and this is represented by the fact that if you multiply this row by this column, the ones occur in disjoint positions, and there is no common neighbor of 3 and 4, which would work as the middle step to go from 3 to 4. So if you perform this multiplication in the third row, the fourth column, result is going to be 0. And I will come back to this next class, but it's not really difficult to show by induction that a to the k entry ij counts number of walks from I to j with precisely k steps. And walks in the graph allow you to repeat, so you can repeat edges, repeat verses. That's walks are very free ways of move in your graph. All right. Now, so what are the things about a graph now? So this is a very simple property of a graph, but why can this actually be useful to certain well, what other properties of a graph are related to this counting of walks? So for example, if I ask you, what is the diameter of the graph? This is somehow encoded in the powers of this matrix, because every time, so I start with A and I examine the first row, for example, I know exactly which are the verses I can reach from the vertex at position 1 in 1 step. I can reach 2 and 5. A squared in the first row, I can reach all vertices of the graph. So by simply looking at A and A squared, I can conclude that from 1, I can reach all vertices in at most 2 steps by simply looking at A and A squared. Now, I also, by looking at A and A squared, I know that from 3, this is not yet the case. Actually, that's a false statement, because I now realize that I cannot reach 4 from 3 in 2 steps, but I could have reached 4 from 3 in 1 step, right? So by looking at A and A squared and looking at where A and A squared have entries different than 0, in fact, I will be able to conclude that I can reach any vertex of the graph from any vertex of the graph in at most 2 steps. And this is exactly the reason, or this is exactly the definition of saying that this graph has diameter 2. So by looking at the entries of the adjacency matrix, which are different than 0, I can determine the distance from any vertex to any vertex of the graph. I can determine the diameter of the graph, for example. So the diameter of the graph is the largest number for which there will still be one entry that has never been different than 0 in all previous powers of the adjacency matrix. Okay, now this is the sort of information which you can observe, which is combinatorial. It has been observed combinatorially by looking at the zeros and one, the pattern of zeros and ones in the adjacency matrix, but somehow this will have a connection with the eigenvalues and eigenvectors of the graph. This is actually what we will see in the next lecture. So there's a question here in the chat: would those matrices be nilpotent if the graph is a tree or a forest? No. These matrices will never be nilpotent, because a nilpotent matrix is a matrix for which there is a number, so that a power of the matrix to that number is equal to 0, to the all zeros. So let's say a nilpotent matrix would be a matrix A, so that A to the k is actually equal to 0 for some k. And this will never occur here, because I'm counting walks, right? So there will always be a number of reaching. Exactly, very good, Eder. So I'm counting walks. I can repeat verses and edges. So there will always be walks of length k in the graph. Simply keep moving back and forth, k times, right? So yeah, counting walks is very easy because of this property of the adjacency matrix. Counting paths is actually NP hard, right? It's NP complete to decide whether or not a graph contains a path with exactly n-1 vertices. So you shouldn't expect powers of the adjacency matrix or any other matrix that you can easily compute by looking at the graph to contain the information of the number of paths. Okay. Another thing that we will explore quite heavily is, so when I wrote this adjacency matrix, there was a choice that was made right in the beginning, which is my decision to number the verses 1, 2, 3, 4, and 5 in this order, and write the matrix in this way. Now, the graph exists, if you want to think of it, without necessarily thinking on this label, vertex labels. I mean, even if you put your labels, why did I decide that this vertex should be actually the first one here in the matrix and not the second? Right, so arguably, if I had decided to, if I had decided to actually number this 1, 2, 3, 4, and 5, I would have written an adjacency matrix of the graph different. So now first row is not adjacent to second, it's adjacent to third and fourth, like that. Oops. right? Second row is now adjacent to third and fifth. Oops, again, third and fifth, and so on. Now, these matrices, of course, are not the same, not equal, but they do represent the same graph, which makes you wonder, what is the catch here? I mean, I'm telling you that I will be relating the graph with eigenvalues and eigenvectors, but suddenly I have a different matrix, and now you're wondering, well, are these matrices, do they have the same eigenvalues? Do they have the same eigenvectors? If not, what's the catch? All right, so this will be the topic of our, we will discuss this next class, and we will also discuss eventually how this interplay between different orderings of the matrix and eigenvalues and eigenvectors can actually be used to determine whether two graphs are isomorphic. Okay, because of course, relabeling versus as I just did can be seen as an automorphism of the graph, or a not automorphism, sorry, an isomorphism of the blue graph to the pink graph of sorts. All right, so I'm simply drawing here the graph 1, 3, 4, 5, 2, and these graphs, the blue and the pink, are of course isomorphic under the function that maps 1 to 4, 2 to 1, 5 to 3, 3 to 5, and 4 to 2. All right, so typically your computer, when you feed a graph to your computer has access to this matrix or this matrix, and somehow you would want to decide whether or not these two matrices represent the same graph. And we will see how this can be cast as a problem that has only to do with matrices, and what eigenvalues and eigenvectors can be helpful to us. Okay, so these are two topics, let's say, two little things that we will be already exploring next class. But as I said, the main topic today is symmetric matrices. They will be very important to us. We want to know what can we guarantee to be true about the eigenvalues and eigenvectors of symmetric matrices. Okay. So our vector space across this course, I will be, let me now move this so that my face is not in front of the, so across this course, we will be assuming, oh, I could have done that. That's actually that. So across this course, we will be assuming typically that our graphs have n verses. So always keep in mind that n is a sort of like special symbol that will typically be used to denote the number of verses in our graph. So of course the adjacency matrix A is n by n, and therefore represents a linear transformation that goes from Rn to Rn. This will be typically our vector space. And this, as you all know, is an Euclidean space. It contains an inner product, and the inner product will be typically the transpose of a vector times the vector. It's exactly what you're used to. A linear operator in any vector space is called self-adjoint if, once you have the inner product, multiplying this operator by a vector and then taking the inner product with another gets the same result if you're multiplying your operator on the other vector for all vectors. Okay, and so what's happening here, if you look at this equation, this is telling you that mv transpose u is equal to v transpose mu, and this thing here is v transpose m transpose u. So this is telling you that for all vectors u and v, this thing is equal to this thing. And then of course, if you choose a basis, so let's say the canonical basis, so you pick u and v to be e1, e2, all the way up to en, the vectors in the canonical basis, you will be, for all pairs of u and v chosen between these guys, you will end up concluding that M transpose Ij is equal to M Ij, right? Simply because Ej transpose M Ei is M Ij, right? For all I and j, this is selecting, sorry, it's the other way around. It's the other way around. This is mji. It doesn't matter. I will be taking all pairs. So this is selecting the jth row of m, and this is selecting the ith column of m, right? So I'm selecting the jth row and then the ith column. So I'm selecting the ji entry. So for all vectors u and v, I can take all the ones here in this basis. If this equality is true, I will end up concluding that this is true for all I and j. Therefore, M is actually equal to M transpose. That's why self-adjoint operators in the real space correspond to symmetric matrices. All right. So M is a symmetric matrix. Symmetric matrices enjoy two key important properties. They are diagonalizable by orthogonal eigenvectors. So actually here there are two properties already. So being diagonalizable is one important property. Having orthogonal eigenvectors is another, and eigenvalues are real is a third. So these are the three key things about symmetric matrices that all of us should know, and I will prove these results now, and actually they will be useful. The techniques used here will be useful. So even if you've seen this proof before, it's important that you actually learn, okay, what's going on, and it would be very nice if as a consequence of today's lecture, you end up able to reproduce this proof upon request. So the eigenvalues of a real symmetric matrix are real numbers. Let's check that first. So assume lambda is an eigenvalue, okay, meaning is it satisfies the eigenvector equation for some eigenvector u. Some of these things could be complex numbers, so who knows? I have no idea. I still do not know what's going on. So I can take the conjugate, the complex conjugate on both sides. M is real and symmetric, so M is left unchanged. Whatever u is an eigenvector. This is the conjugate, so I'm conjugating each entry of u, conjugating lambda, conjugating each entry of u. Therefore, I can conclude that u conjugate is an eigenvector with an eigenvalue lambda. Therefore, what can I see here? I'm taking lambda, I'm multiplying lambda by u transpose u conjugate. The first thing here now is mu, so u transpose is lambda u is mu, so this is transpose. Transposition does not change the eigenvalue, so this is exactly equal to this. Now, what am I doing? I'm taking this transposition, so u transpose, M is symmetric, so M transpose is actually equal to M, right? And then here I have M times U bar, which is, well, U bar is an eigenvector with eigenvalue lambda. This is what I get on the right. So I get these two things. Now, U transpose times U bar is different than 0 because this is a sum of the absolute value of complex numbers, and at least one of them is different than 0. So this is a sum of non-negative things, one of which is actually positive. So this is different than 0, and therefore, if u is not, well, this is different than 0, and therefore it must be that this guy is equal to this guy. Okay, so this concludes that if M has eigenvalues, or for whichever eigenvalue, then let me close it here just a second. If M has eigenvalues, no matter which are these eigenvalues, they must be real numbers. So, and then of course, if you have real eigenvalues, you can simply assume that your eigenvectors are complex numbers, sorry, your eigenvectors are real vectors, because you can compute these eigenvectors by using Gaussian elimination, and m is real, lambda is real, so your eigenvalues are real. Okay, because m minus lambda I times u is equal to 0. So you can simply assume, you can always compute this to be real. All right, let's keep moving. So M, a real symmetric matrix, U and V are eigenvectors associated to different eigenvalues, then they are orthogonal. So I'm now assuming that I have two different eigenvalues, say lambda and mu, and for each of these eigenvalues I picked an eigenvector, U and V, assuming these are real eigenvectors, okay? Lambda is different than mu, so I am going to write this chain of equalities, which again only follows from the trivial fact, from the hypothesis that M is real and symmetric. So I have lambda times V transpose U. I'm now replacing lambda U by mu because of this eigenvector equation. I'm now taking, so this is a number, V transpose mu is a number. The transpose of a number is the number, of course. So I'm taking the transpose of the whole thing, is equal. I'm now applying the transpose to everyone. So U goes to the other side, so it's U transpose M transpose V. M is symmetric, so M transpose is equal to M. Now I look at MV. MV is mu V. So now I have mu V, U transpose V, which again, this is a number, so I can simply transpose it and I get the same thing. So I now have mu times V transpose U. So mu and lambda are different, which means that V transpose U cannot be non-zero. So there's a very easy two results about symmetric matrices. It's very easy to show that the eigenvalues, if any, are real, and eigenvectors corresponding to different eigenvalues are orthogonal. Now the difficult, so I have, well, basically already showed that eigenvalues are real and that eigenvectors are orthogonal, because of course, if eigenvectors corresponding to different eigenvalues are orthogonal, I can, if I have an eigenspace with dimension bigger than 1, I can always choose an eigenbasis which is orthogonal. So for each eigenspace, I have an orthogonal eigenbasis, and if I pick two different eigenspaces, everyone in one of them is orthogonal to everyone in the other. So actually, the difficult thing for symmetric matrices is to show that they are always diagonalizable, meaning they have enough eigenvalues and eigenvectors. Okay. So this lemma is already saying that if M is diagonalizable, then it is diagonalizable with orthogonal eigenvectors. So now let's move to the task of actually showing whether or not M is indeed diagonalizable. So so far, so good. Any questions? Anyone would like to ask a question on the chat? All good? Okay. Oh wow, it's raining. A subspace of Rn, I'm reading here now, is said to be M invariant if whenever you pick a vector in that subspace and you multiply it by M, you are still in the subspace. Okay, so you can think of a matrix or a linear transformation as something that is changing your space, for example, rotating things, or stretching or compressing vectors, or reflecting vectors, doing a bunch of stuff. Okay, certain vectors get changed to others, right? A vector that is only stretched or compressed, no rotation, is an eigenvector. But you could think of this sort of, we can generalize this to larger dimensions and think which are the subspaces which are left unchanged by the matrix. These are called invariant subspaces, or unchanged, or at least mapped to themselves, right? So this M could actually map the entire subspace to something smaller, to a subspace of it, right? This is a key fundamental concept in linear algebra, sometimes overlooked in linear algebra courses. So I would like to really emphasize here that it is very important for you to understand what are M-invariant subspaces, okay? Now, so assume M is a real symmetric matrix. If U is M-invariant, then U perp is also M-invariant. So this is a very important lemma. So U is a certain subspace. U perp, written like that, is this set of all vectors V of your entire space, so that V is orthogonal to everyone in U. Okay? So for example, if U is the subspace in R3 of all things of the form alpha 0, 0, with alpha a real number, this is of course a subspace. U perp will be clearly everything of the form 0 beta gamma, for beta and gamma real numbers. Guys, let me go check if my windows are all closed. Okay, hold on a second. I will be right back. Let's take this as a break. You guys can, let's resume at 1:50. Are there any questions? So far? Oh, good. So actually, let me ask you guys. So have you all taken a course in linear algebra before, linear algebra 1 or 2? Mateus, Eder, Leonardo, Ana? Yes? Okay, good. Okay. So hopefully this is all being a review to you guys. Very good. Okay, let's resume, shall we? Hopefully you're all back. I know it's not 1:50 yet, but anyway. Um, the lemma is telling us that if M is real and symmetric, you get a M invariant subspace. It's orthogonal complement or U-perp, as I've been saying, is also M invariant. And why is this true? So what do I want to show? I want to pick a vector which lives in U-perp, and I want to show that M times this vector is also in U-perp. So by definition, this vector being U-perp means that it is orthogonal to all vectors in U. Okay. Now what do? I pick a vector in U. I pick a vector V in U-perp. I multiply n by V. I want to show that this thing is always orthogonal to U. And this is true very trivially because M is symmetric. Therefore, MV transpose is V transpose M transpose, but M is symmetric, so I can simply forget about this transpose, and I get exactly what I want. Okay. So sorry, not exactly what I want. I get that V transpose is this is equal to V transpose times MU, but U is M invariant, so MU belongs to U, and V is in U-perp, so V is orthogonal to this guy, and therefore this result is 0, which then tells me that MV is always orthogonal to U, to all U in the subspace capital U. Okay, also very easy to show that. So now I get actually to the difficult part here, which is to show that M has eigenvalues. And if I show that M has eigenvalues, I can then apply this lemma over and over and over, a sort of induction, and slowly and surely decompose my space into U invariant subspace, M invariant subspaces, and all of these guys are going to be the eigenspaces of M. So let lambda be an eigenvalue, so something so that the determinant of lambda I minus M is equal to 0. Okay, so lambda I minus M is singular, and therefore it contains at least one non-zero vector in its kernel. Okay, now this is saying that all square matrices N contain at least one eigenvector for each root of the characteristic polynomial. Now, N is symmetric. We know that all possible roots of the characteristic polynomial are real, so I will simply come here and write the characteristic polynomial of N. So this is x to the n plus blah, 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 blah. I know that this thing has all the roots I want in the complex numbers, but I know none of these are going to be complex, because if any of these roots are actually complex, I would be finding an eigenvalue, right, which is not real, and that's not possible. So I know that all the roots of the characteristic polynomial are actually real. Now, this is still not sufficient to show that the matrix is diagonalizable, because there are matrices so that all the roots are real, but the matrix is not diagonalizable. This matrix is not diagonalizable. The characteristic polynomial of this matrix is x minus 1 squared. All the roots of this polynomial are real, they're equal to 1, but this matrix is not diagonalizable, right? Of course, this matrix is not symmetric, but this is, so there's still something to be done. I still need to show that the algebraic multiplicity of the eigenvalues matches the geometric multiplicity of the eigenvalues, and this is done by making use of this lemma 1.3. So what is going to happen now? I take U to be an invariant subspace. I will show that there is one eigenvector of M which lives in the subspace. Okay, now so this lemma 1.4 is the important result lemma, most difficult piece of this proof. All right, So I pick P to be a matrix whose columns form an orthonormal basis for U. Because U is M invariant, when I multiply each column by M, I get something which is a linear combination of the columns. Okay, so now this is the most important moment of today's lecture. This trick will be repeatedly used across this course. So really make sure to understand what's going on here. I have P, you have columns P1, let's say all the way up to Pm. This form a orthogonal base, orthonormal basis for the subspace U. I'm assuming the dimension of U is equal to M. When I M times P, the result is M times P1 dot 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 M times Pm. Multiplying a matrix by another is the same thing as multiplying each column of the matrix on the right by the matrix on the left. Now this thing, Pu, is M invariant, right? These columns belong to U, so this thing belongs to you. Oops, belongs to you. All of these columns belong to you. If they belong to you, they can be written as a linear combination of a basis for the subspace U. So MPJ is equal to some alpha I times Pi, I from 1 to M, because these guys are a basis to U, and this thing here belongs to U. Now, it is not difficult for you to realize now that rewriting each one of these columns as a linear combination is the same thing. So let me now say, let's say that this is, so no, that's okay. This is MPJ. These are going to be alpha IJ. Okay. So now it's not difficult for you to realize that MP1 MPM is now equal to the same P1 PM, but now multiplied by a matrix on the right. And this matrix now, so the first column is going to give the linear combination of these guys, which is equal to the first column. So this is going to be alpha 1 1, alpha 2 1, dot dot dot, alpha M1. Here is going to be alpha 1 2, alpha 2 2, dot dot dot, alpha M2, and so on. So there is a matrix N that I can multiply, post-multiply P by N and get the same thing as N times P. This is very important. This is saying that, well, matrices typically do not commute, but this is saying that if I multiply N by P, there is a matrix that kind of works as a commuting thing from the right. Okay, and this is only true because U is an invariant, so very special. Very special. Okay. Now, in particular, N is equal. So P is a matrix that contains orthogonal eigenvectors, right? So if I multiply P from the left by P transpose, I get the identity, right? Because the eigenvectors. So I'm multiplying orthonormal vectors as columns, orthonormal from the rows. So things cancel out only once. So if I multiply this by P transpose here, this becomes the identity. So N is equal to P transpose NP, and therefore N is symmetric. If I transpose everything here, I get the same expression on the right. Okay, so N is a symmetric matrix, this matrix here is magically symmetric. All right. Now, if U is an eigenvector of N, so I know that N being symmetric contains at least one eigenvector with eigenvalue lambda. And now it's not difficult to realize that if I simply use this eigenvector and multiply both sides of this equation by U, the result is that M times PU is equal to lambda times PU. So any eigenvalue of N is also an eigenvalue of M. And the corresponding eigenvector is P times U. And this thing, oops, there's something, too many symbols here. And this thing is non-zero because the columns of P are linearly independent and U is an eigenvector of something and therefore is different than 0. Therefore, P times U is an eigenvector of M. This is a combination of the columns of P, therefore this thing belongs to U. And this is saying that M has one eigenvector in U. And this is precisely P times U, where U is an eigenvalue of the matrix N. Sorry, an eigenvector of the matrix N. The eigenvalue is lambda. N is the matrix that represents the action of M in the subspace U. Now, this is very, very important. Hopefully, everyone has been able to follow. Does anyone have a question now? I have a question. Good. Now, these four lemmas are exactly everything we need to prove that M is a real symmetric matrix. If M is a real symmetric matrix, then M is diagonalizable by a set of orthogonal eigenvectors, all of them corresponding to real eigenvalues. Why? I left this here as an exercise. Actually, I think this will be on the first assignment, but it is an immediate consequence of these four lemmas if you use now induction. You start with M, you compute, you find one eigenvalue, you compute its eigenspace. That thing is M invariant. You look at U perp. Before you know that this thing is also M invariant. There is one eigenvector of M in there. You compute its eigenspace. You separate it, you find its orthogonal complement, and you repeat, repeat, repeat until you're finally done. All right. So this is the reason why. But now everything is easy here. You already know that whenever you find eigenvectors and eigenvalues, they will be real. You know that they will be orthogonal, and you are basically good to go. All right. So this is the key theorem that will be used over and over and over for us in the next semester. Now, we can get more information about the eigenvectors and eigenvalues of a symmetric matrix. So first, let V1 up to Vn be an orthonormal basis of eigenvectors of M, each corresponding to an eigenvalue. These eigenvalues are not necessarily distinct, so some of these could actually be equal to others, right? Let P be a matrix whose ith column is Vi, so P is the matrix that contains the eigenvector as columns, and capital lambda be the diagonal matrix whose ith diagonal element is lambda I. Then, of course, all of you know that if a matrix is diagonalizable, this is true. You pre-multiply, post-multiply by the matrix that contains the eigenvectors in its inverse. Now, note here that I'm not putting the inverse, but the transposed. Why? Simply because this matrix contains as columns orthonormal vectors, and therefore it is an orthogonal matrix, and therefore P transpose is equal to P minus 1. All right, so everything is good. And it's not difficult for you to realize that this equation here is equivalent to this expression. I mean, This is matrix multiplication, okay? This is, I'm simply now, from this, I go to M is equal to P lambda P transpose. Now these lambdas are multiplying the columns of P, so this is equal to, let's say, lambda 1 P1 dot 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 lambda n Pn times P1 transpose dot 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 Pn transpose. And now I simply realize that this multiplication here is the same thing as multiplying this column by this row, plus this column by this row, and so on. See, the numbers in this column are always be multiplying the numbers in this row, right? Because it's always going to be a row times column. So this is equal to lambda 1 P1 transpose plus dot 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 lambda n Pn transpose. Okay, so this is simply a definition of matrix product. And now the interesting thing is these VIs are normalized. This thing is the projection. This matrix represents the orthogonal projection onto the line spanned by VI. Why is that true? Well, I have V1 all the way up to Vn, forming a basis of Rn. If I take Vi transpose, and I multiply this by Vj, the result is going to be either, well, if J is equal to I, then Vi transpose is 1, and the result is Vi. And if J is different than I, Vj Vi transpose is 0, and the result is 0. So this matrix, acting on this basis, maps everyone to 0 except the vector Vi. You're frowning, Emmanuel. You're my thermometer. You're frowning, so you didn't get something here? Vi transpose times Vj is equal to Vi transpose times Vj. Now this thing here is either 1 or 0, whether I is equal to j or not. Right? So this matrix applying to this basis maps everyone to 0 except for Vi. So this is a projection, right? It is the orthogonal projection onto the line spanned by Vi. That is, Pi squared is equal to Pi, not difficult. Vi transpose times Vi transpose is Vi times Vi transpose Vi times Vi transpose. This is equal to 1, and you're left with Vi transpose. It is symmetric, of course, and it also satisfies Pi Pj is equal to 0. So any sum of these matrices for distinct indices will correspond to the orthogonal projection onto the space spanned by the VIs of the same indices. It's not difficult to see that Pi Pj squared is equal to Pi plus Pj, and that these matrices are symmetric and so on. Right, so everything is working as we would like, in particular because this forms a basis for Rn. The sum of the projections onto this basis, because these are all orthogonal projections, is the projection of Rn onto itself, which is the identity matrix. So this is true. You can check that this is true using several explanations. For example, you can check also that if you multiply the sum by a particular Vj, the result is Vj. and this is true for all j. So if something is true for all elements of a basis, you know, if something preserves all elements of a basis, you know that this matrix must be the identity matrix. Okay. Exercise 1.8, very interesting exercise. If the PIs are orthogonal, assume the PIs are orthogonal projections. Given orthogonal projections to U, show that the sum of them is an orthogonal projection if and only if P1, P2 is equal to 0. So if P1, P2 is equal to 0, then it's very easy to see that if the PIs are orthogonal projections, then this is an orthogonal projection. The difficult thing here is to show that if this is an orthogonal projection, then it must be the case that P1, P2 is actually equal to 0. So the converse of the statement that I just used in this paragraph here is the difficult thing in this exercise. For two matrices, it's actually not that difficult. But for K matrices, then it's actually tricky. So this is a sort of difficult exercise, the second part here. But the first part is easy. Now, let me just sort of like mention to you how this goes. So I'm assuming that P1 plus P2, so to be orthogonal projection means that these PIs are all symmetric matrices and that the squared is equal to themselves. So I'm assuming that P1, P2 squared is equal to P1 plus P2. Now this thing here is equal to P1 plus 2 P1 P2 plus, squared. Now I come here, I erase this square, right? And then of course this expression here on the bottom is equal to this expression here on the top, if and only if this thing here is equal to 0. So why is this difficult? What did I do? Why? Why is this supposed to be difficult? The catch is that this thing is not true, because hidden in this equality is the wrong assumption that P1, P2 is equal to P2, P1. That's true for numbers, but not necessarily for matrices. So in fact, the answer here should have been P1, P2 plus P2, P1 plus P2 squared. Now, okay, these squares disappear, but now why this thing here equal to 0 implies that P1, P2 is equal to 0. It could be that they're just minus them each other, right? It could be that P1, P2 is minus P2, P1 and non-zero. So this is the difficult thing here that I want you guys to think a little bit and try to show that. Okay.
I was just waiting for this exercise to appear.
Oh yeah, that's my favorite exercise. Now, M is a n by n symmetric matrix with distinct eigenvalues. So now I am assuming that I have already compiled my similar eigenvalues. I have my high dimensional eigenspaces. So I will be assuming typically across this course that my matrices are n by n and that my eigenvalues have been listed from 0 to d. Don't ask me why, I'm simply used to this. Please get used to this as well. So when we write this second equation from the statement of corollary 7 point, so when we write this, and I group the similar eigenvalues together, and I sum the orthogonal projections onto the lines that form the eigenspaces, I end up getting the projections onto the eigenspaces. So that equation from corollary 1.7 actually is equivalent to this. So this is what I will always referred to as the spectral decomposition of a symmetric matrix. These are the eigenvalues, they are real. These are the projections onto the eigenspaces. Okay, so these things each one of these, so let's say the rth eigenspace has eigenvalue theta r. Let's say that this eigenspace has orthonormal basis, let's say v1 all the way up to vk. So this ER is equal to V1 transpose plus dot 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 VK transpose. Okay, it's easy to see as a consequence of everything that we've been discussing so far that the sum of the ERs is equal to the identity matrix R from 0 to D, that ER times ES is equal to ER, if R is equal to S and 0 otherwise. Okay, so this is the spectral decomposition of a matrix, a symmetric matrix, and we will be looking at this thing over and over and over across this course. So this is an example of a symmetric matrix, and I'm asking you to find its spectral decomposition. So there's a hint here. I want you to instead of so typically, how did you guys learn how to compute the eigenvalues and eigenvectors of a matrix? You write the characteristic polynomial, you find the roots, you perform Gaussian elimination, you find the eigenvectors. Now, this is a very stupid way of finding the eigenvectors and eigenvalues of a matrix. No computer, algorithm, person with a sane mind finds eigenvalues and eigenvectors in this way, simply because if you write a polynomial of degree 4, it's much harder to compute its roots than it's actually is typically to guess the eigenvectors of a matrix. In this particular case, it's much easier to guess which are the eigenvectors of this matrix and find the eigenvalues, and then express this matrix as a sum of things which are eigenvalues times projections, so that the projections satisfy this thing. Okay, try that. Now, for any polynomial p, whenever I write, so let's say px is the polynomial an times x to the n, not n, sorry, let's avoid n as a protected symbol in this course. K from 1 to, I don't know, m, ak x to the k. Given a polynomial like that, p applied to a matrix is the matrix given by k goes from 1 to m, ak m raised to the power k. So why is it true that if I apply the polynomial to the matrix M, I get the spectral decomposition with the same projections onto eigenspaces, but the polynomial is applied to the eigenvalues? Well, it's not difficult to convince yourself that this is true if you simply look at m squared. M squared is the sum of the theta r from 0 to d, sum of the theta r from 0 to d. Now this thing here is the sum r and s going from 0 to d of theta r theta s times er es. Now when r and s are different, this thing is 0. When r and s are equal, this thing is er, because this is a projection. So the result here is the sum r from 0 to d of theta r squared er. So m squared, the square of the eigenvalues, same projections. Not difficult now to believe that any power, this is going to happen, multiplying by, this is a linear thing, multiplying by constants, you can simply move things out. So any polynomial applied to the, and that is also if the polynomial is the constant polynomial, right? If the polynomial is the polynomial that maps px goes to 1, if this is the polynomial, I am assuming that this means that Pm goes to the identity matrix. Right, so constants are identity matrix, right? So it's not difficult with this understanding to believe that whenever you apply a polynomial to M, that's exactly the same thing as applying the polynomial to each one of the eigenvalues. Okay. Okay, now let's look at this exercise 1.1. If M is a symmetric matrix with spectral decomposition just like you see here, right? What is the minimal polynomial of M? What is the minimal polynomial? The minimal, so if I have a matrix M, the characteristic polynomial is always going to be the determinant of x times I minus m. The minimal polynomial is defined as let's say px of smallest possible degree, non-zero, non-identically zero, leading coefficient 1, leading coefficient equal to 1, so that P applied at M is actually equal to 0. Right now, so these two things are typically different. Well, and it's actually a theorem, not trivial theorem in linear algebra, that for all matrices, the minimal polynomial divides the characteristic polynomial. Okay, but for symmetric matrices, this is actually easy. Okay, why? Well, because by looking at the spectral decomposition here, and by knowing that when you apply the polynomial to M, you're applying the polynomial to the eigenvalues, and because the ZRs are all independent, they're projections onto independent things, the only way this thing can be equal to 0 is if P applied at theta r is equal to 0 for all r. And this defines a polynomial. The polynomial of smallest degree and leading coefficient 1 that satisfies this property is precisely the product r from 0 to d of x minus theta r. And we know that these theta r's are the eigenvalues of the matrix. We know that the characteristic polynomial of M is precisely the same thing, but with these factors raised to their multiplicities. So it's actually easy to check now that the minimal polynomial divides the characteristic polynomial for symmetric matrices. Very easy. Okay. Now, how can you prove that for each ER projection onto eigenspace, there is a polynomial of degree D that maps this matrix M to the projection? Well, it's simply because if Pm is equal to ER for some R, this means that P theta S is equal to 0 for all S different than R, and P theta R is equal to 1. Right? Now, you can always find a polynomial that assumes values in a set of distinct numbers. There is a formula for that. It's Lagrange interpolation. In this case, it's actually very easy to come up with the expression here for the polynomial PR. I will leave that to you guys to find that on your own, but it's very similar to this, except that, well, for all eigenvalues, there will be a term that looks like this, except for theta r, but then it's not difficult for you to fix on top and the bottom, okay? So I'll leave that to you as a sort of like easy exercise. Now prove that two symmetric matrices M and N commute if and only if they can be simultaneously diagonalized by the same set of orthonormal eigenvectors. Now, how do you do that? So I am assuming, so I want to show that Mn is equal to Nm if and only if they have the same set of orthonormal eigenvectors. If and only if there exists P so that P transpose MP is equal to some lambda, and this is a diagonal matrix, and P transpose NP is equal to some, I don't know, gamma, and this is also a diagonal matrix. Now, one direction here is trivial. Which one is it? Or both, but one is more trivial than the other. Well, if you assume that this is the case, so if P transpose, then you can see, so what is the trivial thing here? The trivial side here is that, well, assume that this is the case, so M is equal to P lambda P transpose, N is equal to P gamma P transpose, and therefore Mn is equal to P lambda P transpose, P gamma P transpose, but P transpose is the inverse of P because these are orthonormal eigenvectors. So this is the identity matrix, and the result is P lambda gamma P transpose. These things are diagonal matrices. Diagonal matrices always commute. So this is P gamma, and then I can put this thing back in the middle. P transpose P lambda P transpose, and this is N times N. So one direction is very easy. The other is an exercise for you guys. Okay. Second part of the exercise. Is it true that if M and N commute, then there is always a polynomial P that maps M to N? Or they have the same set of eigenvectors? How could this not be true? Well, M times the zero matrix is always equal to the zero matrix times M. Is it true that there is always a polynomial that maps the zero matrix to a given matrix M? Not really, right? Oh, there's something off here. What is it? So I want you to, well, characterize what else you need to observe to guarantee that such polynomial P exists. I mean, clearly this is not true in general, as here you have two matrices that commute, and I cannot do this, right? So think a little bit about it. Let A and B be matrices, not necessarily square-shaped, so that both products AB and BA are defined. Then prove that the trace of AB is equal to the trace of BA. This is actually very easy. And it follows straightforwardly from the definition of matrix product and the product of vectors. Conclude that if M is a symmetric matrix with eigenvalues lambda 1 to lambda n, then the trace of M is the sum of the eigenvalues. right? So this is basically following from this, okay? So it's not supposed to be difficult at all, right? And in fact, as a consequence of whatever this exercise is related to, I want you to also realize that the dimension of the theta r eigenspace is equal to the trace of this projection matrix, right? So this is everything I wanted to say about symmetric matrices. Everything that will be, I mean, the basics of the stuff on symmetric matrices that will be useful to us. The basics. Next class, actually, we will see a non-trivial result about symmetric matrices that probably you haven't seen before, unless you've taken a course in spectral graph theory or something similar. But for the basics, this is everything I wanted to say. This, as I assume, has worked as a review for most of you if you've taken a course in linear algebra 2. If you haven't taken a course in linear algebra 2, I guarantee that everything is here. I know that this was probably a little bit too fast, but you can review these lecture notes, study them carefully, solve the exercises, write a couple of examples by hand, and I am sure that it's going to be possible to understand what's going on. Okay, if you still are too lost on what's going on with the symmetric matrices, talk to me, let me know, send me a message after class, and I'll try to help you. So this is the beginning of the course. It's very important that these concepts are well understood by every one of you guys. Eigenvalues, eigenvectors, orthogonality of eigenvectors, spectral decomposition, invariant subspaces, commuting matrices, as I just mentioned, connection between trace and dimension that I just showed you on the bottom, minimal polynomial, how to write the eigenprojectors as polynomials in the symmetric matrix. All of these things will appear recurrently across the course, okay? So let me know if you have any questions. I think the assignment for this week will contain some of these exercises that we just saw here. I think I'll probably post this assignment already today or tomorrow. It will have, I don't know, 4 exercises, I think. And then you guys will have the weekend to kind of work a little bit and check. Next class, we can go slightly slower with this topic of adjacency matrix. I will review the things that I was mentioning in the beginning of the lecture today about counting walks, about determining whether two graphs are isomorphic or not, not that, but what does how can you define isomorphism between two graphs as a matrix operation, and some of the basics of what we will be studying later. Okay, so thanks for coming, and I'll see you all on Thursday.